When we talk about systems in science, like a couple of systems I can think of. Your endocrine system is a series of glands that work together to regulate the hormones in your body. Your respiratory system is a series of organs that work together to oxygenate your blood, basically like gas exchange, exchanging oxygen and carbon dioxide in your system. If we think about systems in government, so the system of government that we have is the way that all the different parts of our government work together to help run the country. So when we think about a system, we're thinking about how things interact together, how things work together to perform a function. Well, we have systems in algebra. So in algebra, a system is when we look at more than one equation and look at how they interact with each other. So in Algebra 1, we're responsible for knowing how two equations work together, two equations or inequalities. When we think about systems, the reason we need a system is because we're looking at how so like for example, like we might have two equations that describe the same thing, that use the same variables. Well, if I have one variable, so let's say I had the equation, let's say I had 8 equals 3x plus 5. Okay, well I could solve this equation and I would find out that x equals 1. There's only one variable, so I can use that one equation. Well, if I change that into y equals 3x plus 5, there is nothing I can do to figure out. I can set this in terms of y and in terms of x, but I can't figure out what either x or y is worth because I only have one equation. If I introduced a second equation, I could see where those two lines cross and I could say, what do these x and y have in common? What x and y do these two equations have in common? That's what a system is. A system is, instead of just looking at one equation, I'm going to look at two equations. So let's say like 2x minus 3y equals 7. And what coordinate makes both of these true? Okay? So that's what a system is. A system is two or more equations and how they interact. Okay? With linear functions, in Algebra 1, we're only responsible for two variables, we're responsible for two equations in our systems, and we're responsible for only linear systems. Now, when you get to later classes, you're going to have to deal with other types of systems, but for now, we're only looking at linear systems with two variables. Now, we're going to do equations by graphing. We're also going to do inequalities by graphing. But the solution to a system is a point that will make both equations true. So we have three different types of solutions we could have. We could have one solution, we could have no solution, or we could have infinite solutions. So we're going to actually look at two equations, and we're going to see what the solution to these two equations is. Okay? So the two equations we're going to look at are y equals negative 3x minus 5 and x minus 2y equals negative 4. Now, this first one is super obvious. It's really easy to tell because it's in slope-intercept form. It's already graphable. Okay, so I know that my slope is negative 3. My y-intercept is negative 5. So I'm going to start at 1, 2, 3, 4, 5 at negative 5. I could fall 3, run 1. That takes me off the graph. So I'm going to continue that pattern, rise 3, back 1. On the graph. Now with systems, another thing about systems, it is really, really important that our lines be graphed precisely. So like we can't draw jankety lines. They need to be really good, really like clearly drawn lines, exactly how we want them. Now this does not mean they have to be perfect, but they have to be as close as we can get them. So we want to use a ruler and we want to make sure that we are plotting our points precisely. Okay, so that's the first one. Now the second one's a little harder because this one's in slope-intercept form. Slope-intercept is not a graphing form. So in order for us to graph it, we have to transform it somehow. We can use the cover-up method, which is my personal favorite. So that would be where I would cover up the x, and then I solve negative 2y equals negative 4. I get y equals 2. So that means my y-intercept is, 0, 2. And then I cover up the y term to find my x-intercept. Well, it just says x equals negative 4. That means my x-intercept is negative 4, 0. So I put a point on both of those, 0, 2, negative 4, 0, and I connect them. And again, I try to be as precise as I can when I connect these points. I want it to go as precisely as possible. Whoopsie, I might have gone too far there. Precisely as possible through both of those. Okay? Now, I can see where they cross. Just FYI, if I wanted to solve it by putting it in slope-intercept form, I would say x minus 2y equals negative 4. I would subtract x from both sides. Negative 2y equals negative x minus 4. Divide everything by negative 2. And I get y equals 1/2 x plus 2, which matches I start at 2 and I rise 1, run 2. So that actually still matches. Okay. Now, when I look for a system, I'm looking for how these two lines interact. Well, I can see right here that they cross so they have one solution, and because they cross in one place, and that one solution is at negative 2, 1. So they have one solution at negative 2, 1. All right. Now, there are other ways that I can actually solve this problem. So first of all, this is the obvious way. So if they give me a graph with two equations plotted, I'm going to look for where they cross or how they cross, okay? I can also put them in my calculator. So since I have the slope-intercept form of the second one and the first one, I could go to y equals, and I could, here, let me put this over here so we're not getting too much reflection. I can put them in, that's craziness. I can put them in here, and I get negative 3x minus 5 for y1. For y2, I'm going to put in 1/2 x plus 2, and I can look at the graph. Okay, so the first thing I can do is I can look at the graph. Now, when I look at this, I'm sure you've noticed that on our calculators, the graphing part is not as precise because it's a poor quality display. So there's two things I can do. Of course, I could go to the table, so second graph, and I could look at the table of values. And I'm looking for the row where y1 and y2 are equal, if there is one. Well, I see it right here. How would I prove that I had found it there? Well, I would do x, y1, and y2, and I would show what I saw. Well, I saw negative 2, 1, and 1. Now, what this means is x, y is my solution. So I create an ordered pair out of the first two columns, which gives me the same exact solutions I have here. Now, I can also get the calculator to do this for me. Okay, so get over here again. If I go to the graph again, there's tools, there's a trace button. Now, trace lets me kind of like move along the line, and when there's two lines, I hit up to move back and forth. I hit left or right to move along the line, and I hit up and down to move between the lines. And I can get pretty close to the solution, but I can't find exactly what it is. So if I want to find out exactly what it is, I can hit second trace. You see this button here, intersect? That's going to tell me where they cross. So I hit 5. And then I'm going to hit enter, enter, enter. The first enter hits the first line, the second one selects the second one, and the third one tells me to guess. I just hit enter, enter, enter. And it tells me the intersection, x equals negative 2, y equals negative, y equals 1. So I could also say here, x equals negative 2, y equals 1. Okay? So that's how I do it in the calculator. Now, sometimes they're not going to give them to you all in one 3-column table. They might give you 2 tables. So let's say they gave you this. Let's say they gave you 2 tables, and they gave you this. So negative 2, 1, negative 1, 2, 0, negative 5, 1, negative 8. And then the other table was negative 5, negative 4. I'm sorry, negative, what does that even say? I can't even remember. Oh, negative 1/2, negative 4, 0, negative 3, 1/2, negative 2, 1. Well, I've got 2 tables. So in this case, I'm going to look for the ordered pair they have in common. Well, they both have a negative 2, 1, which means that the ordered pair that both of these have in common is negative 2, 1. That's how we find it by graphing. Okay? That's one solution. So one solution is the most complicated one. Now, we might also see something where they never cross. So no solutions means the lines never cross. And that means that they're parallel. So we already know that lines that have the same slope but different y-intercepts are parallel. Well, if I look at the graph, it looks parallel, but there's kind of an optical illusion. I don't know if you see it too, but it kind of looks like it's bulging right here in the middle where it crosses the lines. I think it's parallel, but I want to confirm that it is. And so the way I do that is I go into the table. Well, I can tell because they have the same slope. But if I'm still not sure, I can look at the actual values. So 21 minus 13 is, I don't know what that is. What is it, 8? 18 minus 10 is 8. 15 minus 7 is 8. 12 minus 4 is 8. 9 minus 1 is 8. These all have the same difference. And because they have the same difference, that difference in common, that means they're the same distance apart, which means they're parallel. So if all my y1s and y2s are the same distance apart, then they're parallel. Okay? The last one we might see is infinite solutions. So let me just show you. Let me make one up for you that's infinite solutions. Like this, I think. That looks good. Okay, these are two different equations, but when I graph them, it graphs the first line, and then the thing keeps going like it's doing something, but it never graphs another line. When I look at the table, what I see is all of the y1s and y2s are equal. That's because it basically graphed the same line. These two lines simplify to this. These two equations simplify, well, expressions simplify to the same expression. So negative 4x plus x is negative 3x. 3 minus 8 is negative 5. So these two lines, they're different equations, they're different expressions, but they simplify to the same thing. And what that means is when this line graphed, it graphed the line, then it graphed the exact same thing. So what you're seeing is it shows one line because they simplify to the same line and they literally graph right on top of each other. Okay? So that means the table is showing all y1 and y2 values are equal. That means that no matter what point I put into this table, all of them are going to give me, no matter what x I plug in, I'm going to get the same y's. That means every solution. I have infinite solutions. And sometimes we see that as infinitely many solutions, or we see it as all real numbers. All right, that's all I have to say about graphing. If you have any questions, please feel free to let me know.